All right. There's homework 5 that's available on the web. Hopefully it'll be available in class in a couple of minutes or half an hour or so. The final exam, I'm as unhappy with the date as you probably are. It's the last day of finals. I don't choose it. Right, the registrar just chooses it based on the schedule. So I guess they figure if you have the Monday slot at 9 o'clock, the very first earliest point of the week, why not give you the exam on the last day? So and it's at 9 a.m. Mud 1024. So at least it's not the last of the last exams. Any questions on the homework or course? No? Okay. So this next homework number 5, is actually, it turns out to be a short one. There's 3 questions. 2 of them will be based on the material we're doing today. 1 of them will be based on the material next Monday. I won't be here next Monday, but Professor Meeser will cover the class. So, and the material that he'll cover is part of the course. So. Alright, see how that goes. Okay. What we're going to look at today is spanning trees for lands. Okay, so if you recall, we had these lands connected by some sort of bridging device, right? This here is a wire of land. We connect up a bunch of machines. Right, and remember these devices, they could be switches or hubs. If they're switches, they can learn. Word to word packets. Okay, and a lot of times, if you sort of imagine Columbia, you may have a lot of these lands scattered all over campus. Okay, like so. And then you start connecting them up with switches, and who knows, maybe sometimes the way things are connected up with switches, it's not necessarily a tree, right? They can be connected up in some weird arbitrary way. Okay, so the switch to line connections need not form a tree. You can think of a LAN as just a wire, okay, that's connecting up a bunch of machines, and then, 2 engineers at 2 different edges of the wire might choose to connect up a switch to that and hook it up to their LAN, and who knows, in the end you may get cycles. Okay, so wire cycle is bad. Okay. Well, here's the easiest example. Remember that Go ahead. If I had a nickel for every time I heard that one. Come on. Just, yeah. Got your name in it? Yeah. All right. So wire cycle is bad. So if you remember, what's going to happen is each of these wires is a broadcast medium. Okay. So if I send a packet out on this, if I'm a machine over here and I want to communicate to a machine over here, and I send a packet out onto this wire, okay. Suppose both of these switches think that it's their responsibility to carry the packet to the next wire. Okay, well then this one's going to carry, let's assume there are no collisions. This one's going to carry the packet to the next wire, and it's going to be broadcast on this wire by this switch. And similarly, the packet's going to be broadcast on this wire by this switch as well. Okay, so you send one packet in, you get two packets out. Okay, each of these switches picks up these two packets and forwards it onward. All right, so now you've got four packets. Four identical copies of the same thing. Right? Let's say the switches are smart enough to know where to forward the packet, but they don't look to check it's a duplicate. They don't remember packets they forwarded in the past. So every time, well, why did I draw 8? 4. And then finally, by the time it gets here, 8 copies are sent. Okay, so the problem is, well, in this case, it's not even a cycle. I should say, well, you have a cycle in a sense. Okay, so you don't want multiple paths between LANs. Ideally, what we'd want to do is turn off one of these switches between each LAN. And now only one copy of the packet will be forwarded from one end to the other. Right? I forward a packet onto this LAN. This switch picks it up. It puts one copy onto this LAN. This switch picks it up and puts one copy onto this LAN. This switch picks it up and puts one copy onto that LAN. Okay? Everybody with me so far? Okay. Now, here's the thing. I have to explain a little bit of what happens in practice. These switches are very lightweight devices, meaning I'll just walk up to my LAN, plug in the switch, hook it up to another LAN, and I'm done. So there's not a lot of coordination or planning, or you don't want the system to involve a whole lot of coordination or planning. It should be easy to hook up it should be easy to hook up these switches. So the switches should not require programming / a lot of manual configuration. Suppose ASYS wound up connecting things up in this topology. You don't want to have to send a worker out there to realize, oh, we didn't need this switch. Let's turn it off. And suppose this switch failed. Okay, it would be nice if the worker did not have to manually turn back on this switch over here. Okay, if just when there was realization that the communication was breached between these points, the other switch would turn back on. Okay, so basically, I want these switches to be ready. They turn off if they're providing redundancy. They turn back on if something else has failed, and they can cover for that other switch. Okay, so we're going to look at a spanning tree algorithm. Used for this purpose. Okay, and well, we're gonna wind up using shortest path trees, and the reason is not because you want the shortest distance from whatever we're going to choose to be the root to these other nodes. The reason is because it's easily distributed. Okay, like we saw Bellman Ford. Okay, whereas we never saw a distributed algorithm for a minimum spanning tree. The algorithm that we saw, the two algorithms are both centralized. All right. So first, let me drop a concrete example. Actually, let me use one I have in my notes, otherwise. Or do I have a good one in my notes? Yeah. Okay, so here's an example of a topology. Right? What we're saying is we want to have all the lands be connected to one another, but only have one path through the lands. Okay, so for instance, from a global perspective, it's pretty easy to pick the path. Right? You could choose this. Okay, so in fact, this switch, remember switches can configure whether or not it forwards out on a given wire. So it would not be forwarding on this wire. And this now connects, this LAN is connected to this LAN is connected to this LAN, and this LAN is also connected to that LAN. So there's a path between every pair of LANs, right, using the thick edges, and there's only one path. So again, this switch, these interfaces are turned on. This one is not. Okay? Everybody follows? I want to, well, let me say this. I have switches. Okay? I can choose to have this switch forwarding packets from one LAN to another. And I can choose the interfaces on which that switch forwards packets. Right? So if a packet comes in here, I can choose to only have that packet forwarded out on this interface. So I can turn on some interfaces and turn off others. Now, I want to have, and you put a packet on any of these LANs, I want to have a path to the other LANs. Right? So if you have a packet that starts here, I need a path to send it over here. And I don't want more than one path available because I'll get this duplication problem. So for instance, if I have this switch turn on both of its interfaces, this switch turn on both of its interfaces, and this switch turn on its top and its bottom interface, then all my LANs, there's a path between every pair of LANs. Right? If I want to get from this LAN to this LAN, I use this switch to carry the packet from here to here. If I want to get from here to here, I use this switch to carry the packet from here to here, and then this switch picks it up and brings it here. If I want to get from here to here, right, this switch to here, this one to there. There's a path between every pair of LANs. And these other switches, I turn them off. And I turn off this interface. Okay? Okay, so what's the algorithm that you run in a distributed fashion? So every switch is going to participate in this algorithm. Okay, and here are some properties of the switches. Okay, they can turn on interfaces. And they know when another switch shares the same LAN. This is 1, 2. Or is attached to the same LAN. Okay, and they can do this by a local broadcast of a special packet. Okay, so switches themselves can generate packets, right? They're usually used for carrying packets from one point to another. But for the purposes of constructing this spanning tree, they're also going to be able to send packets. So for instance, if these switches want to learn about one another, this one can send a packet onto this LAN, and this one can pick up that packet, right? And if these special packets are not forwarded any further, then this switch and, what's a good example? This switch and this switch would never communicate directly with one another with one of these special packets, right? Because this switch would forward its packet onto these two LANs over here, and that special packet wouldn't be forwarded any further. This switch would never pick it up. So they know that they're not on the same LAN. Okay? So that they can learn on the same LAN. And also, each switch has a unique ID number. Okay, so just imagine when you build these switches, you program each one with a unique ID number in the factory, so you can distinguish between any pair of switches. So here's the algorithm. So first, choose a route. Sorry, before I get there. And also, the administrator can assign weights to the LANs. Okay, so for instance, this wire could have weight 3, and this one could have weight 2, and this one could have weight 4, and this one could have weight 7. In practice, they're usually just set to 1. But they could be assigned weights. Okay, and then the distance between two switches, or let me say it this way. The graph on which we will build the tree has switches or nodes, and edges connect two switches that can communicate on the same LAN. That both connect to the same LAN. And the edge weight is the weight of that LAN, the weight of the connecting LAN. Okay, So for instance, in this graph that we're going to draw, this switch and this switch are connected by this LAN with weight 2. So in the graph, you would have these two nodes representing those two switches and an edge of weight 2. And you'll notice that this switch and this switch are connected by two different LANs. So just think of that as drawing two different edges between the switches. Oop. Okay. Everybody clear on this far? Okay. So in the algorithm, first you choose a root node. Okay, to be discussed next. Okay, then all switches run Bellman Ford. Okay, and they construct the shortest path tree. So for instance, in this graph here, let's say this node is chosen as the root. Okay, then what would the shortest path tree look like? This guy, in this example, right? This node is a distance 2 from the root. This node is a distance, these nodes are distance 3 from the root. Right? And then we could go either way, either through here or through here. Actually, we've already reached all the nodes. All right, so this is what the shortest path tree would look like. Right, that's the shortest path tree that connects all those nodes. Okay? Now what we're going to do is each switch is going to label each interface. And labels the interface connects it to the LAN. That connects it to the root of the shortest path tree. With an R. Okay, so and the root labels all interfaces are. Well, let me think about that for a second. Yeah, just say that. Root labels all interfaces are. Okay, so this is the root node, so it labels all of its interfaces R. Okay, and then all these other nodes, they label the interface that points toward the root with an R. Okay? All other interfaces are labeled D or S in the homework. I made up the second question really late last night, so I just put S. I didn't remember the algorithm used D instead of S. So you see in the homework I said S, but for all other purposes we're going to be using D. Okay, so all other interfaces are labeled D. Is that it? Yeah. Okay. Any questions so far? Where are we up to? Step 5. Okay, now for each switch broadcasts on each local LAN its ID number. Okay? And turns off its interface if some other switch with lower ID, each switch broadcasts across each interface labeled D. Its ID number and turns off its interface if some other switch with lower ID is broadcasting on that LAN. Okay, so for instance, let's give these switches ID numbers. So 2, 7, 5, 4, 8. Okay? So what I said is every switch is going to broadcast to every LAN on which its interface is labeled D, its ID number. Okay? And then it's going to turn off if some other switch with lower ID number is broadcasting on that LAN. So for instance, 7 and 8 are both going to broadcast on this LAN down here, right? And they're going to be exchanging their ID numbers. 7 will see it's got the smallest ID number on this LAN. 8 will see there's a node with a smaller ID. So 8 will turn off this interface. Okay, on this LAN here, you've got 7 and 5 and 4 broadcasting on it, right? So 5 and 7 will turn off their interfaces. And is that it? This LAN, everybody connected to it is an R. This LAN, everybody connected to it is an R. So that's it, you're done. Okay? And at this point, you should have your tree. With this property that there's one path between every pair of LANs. So for instance, this LAN and this LAN, the path goes through node 7, through node to node 2, to that LAN. Oh, wait a second. Yeah. Wait. No, I have a loop. Oh, no, I don't. Right? You're not broadcasting on this LAN over here. Right? So the only path is through node 7. It doesn't go this way to this LAN, through node 2 to that LAN. Okay, so there's a path between every LAN. There should be a unique path. Yeah.
Is there any specific way you name the switches? Or you can just name them randomly? I mean, the IDs.
The IDs are given arbitrarily. They're actually built into the switch. If there's time at the end, I'll explain that in a little more detail. But yeah.
Why do the switches leave node 4? Why does it leave open? It's not being used.
So why is this left open? No, this is the path. If you want to get from this LAN to this LAN, you'd go this way. And it's the unique path between those two LANs. So the algorithm is a little bit magical, and actually, so let me make two observations about it. Okay, and then the point is, yeah. Now you have one path between each pair of lanes. So the second homework question is to prove that this is what winds up happening, and the homework sort of gives you some hints on how to step through the proof. But let me give you intuition as to why this works. So here's one observation. Okay, every LAN you may have multiple switches connecting to it, but at the end there will be at least at most one D. Attached to the LAN. Right? Only one interface labeled D will be attached to the LAN and active. Right? Because we turned all the others off. That's what we did in step 5. We broadcast everybody who's connected to a LAN with a D broadcasts on that, and everybody gets turned off except one. Right? It's got at most one D turned on. All right. Okay, an observation 2. If you look at these LANs, right, we had some root node and a bunch of edges labeled R. Oh, sorry, a bunch of interfaces labeled R. Okay, and the point about these is R interfaces head toward the root. So any interface, let's see, meaning to go from any switch to the root switch follow the R interfaces. So think about it. If I want to, the way we chose the R interfaces, if you remember from this picture over here, is they're the ones on the shortest path tree that take me toward the root, right? So if I follow a switch's R interface, it's going to take me to a LAN that takes me closer to the root, right? And with the exception of the last hop, which is the root itself, okay, I'm always going to be taking this R interface, putting me on a LAN, and then to get off that LAN, except for this last step, which is the root, I'm going to have to take a D interface to get to some next node. I just take the D interface that's turned on. There is always one on that LAN that takes me to another switch. And if I follow that one's R interface, I just keep moving closer and closer to the root. Right? Follow the R interfaces that take you to a LAN. And take the on D interface. That moves me closer to the that moves me to a switch closer to the root. Yeah, Ron.
Toward the root?
Yeah, R interface is head toward the root. Yeah. And this is a colon. To go from any switch to the root switch, follow the R interfaces that take you to a LAN, and take the D on that interface. Take the on D interface that moves me to a switch close to the root. So you're always going to go R, but if I want to get from this switch to the root, I take the R interface that takes me to a LAN. This LAN has to have some switch attached to it that has its D interface turned on, unless it's already connected to the root node itself. So I take that D interface that takes me to another switch, which has an R, which is always so every step I'm taking a switch's interface that's on the shortest path towards the root, takes me to a LAN, and on that LAN there's another switch that takes me toward the root. So I'm always moving from LAN to LAN that's toward the root. Okay, so that's why it's connected, and basically the root edges always take me. The root interfaces, the R-labeled interfaces, always take me toward the root. So they can't form cycles either. If you had cycles, you'd have to be taking a series of R interfaces, and they wouldn't always be moved toward the root. At some point, you'd move toward a node that's further from the root than the previous. Right? If I follow this path from hop to hop, if I follow this procedure, then I will wind up, every time I follow a root interface, I wind up on a LAN that's connected to a node, another interface that's closer to the root in terms of that shortest path tree. Yeah, Ezra. You follow the R to get to the root. No. I mean, so for instance, well, this example was sort of short. No. I mean, so for instance, this guy's R interface takes him to a LAN, which then can be picked up by root. In this case, everybody's at most. I could have had another switch here. This interface would have been labeled R. Okay, and this would have been its path to the root, right? So you take the R interface, it puts you on a LAN. That LAN is connected to another switch who's got a D interface, and that's turned on. And when you follow that D interface, leads you to that switch, and through its R, you're closer to the root. That's sort of the process. Okay, and homework, you prove this more formally. Okay, so the only challenge left is to choose root of the tree. Okay, so there's questions.
I'm going to take the on-D interface. Like, let's say in this pattern you have node 7 or something, and you want nodes 2, right? So you would put the R, but then there's no D would you connect to.
Oh, so you know, yeah. I made a mistake. It's not irrecoverable, but where did I do it? Yeah, let me just make this one small change. It'll make things a lot more clear and consistent. The root labels all interfaces D. All right. The root labels all its interfaces D. So this instead of being R should have been a D. The root node itself, everything else stays the same. I said the root node labels all its interfaces R. They should have all been labeled D, and nothing changes. Okay. Yeah.
When you added the bottom node just now.
If we start everything over and we try to make the shortest path tree, wouldn't the root connect to that bottom node? Would the root connect to the bottom node?
I mean, if you had two groups and then you made the SPT with the new graph, you have a shortest path.
You have the shortest path from 2 to that bottom node, right? Okay. Yes. Right. Here's the thing.
We use the shortest path algorithm, and we're using this algorithm just to help us build a tree. Okay, and then the tree that we wind up using is not the same as that tree. The purpose of that tree, that first tree that we build using this path algorithm, is just to mark every node is going to have an interface marked as an R. That's all we're using this shortest path tree for. Okay, so I don't know if the shortest path tree would go through this node or through this one. Okay, but in any case, this is the interface that would get marked with an R in this example, right? I mean, clearly, this node would take this interface to get to this LAN, which would take it toward the root of the tree. Okay, and at the end of that algorithm, right, you've got the shortest path tree where every node is clearly connected. There's a path to the root, and it's a tree, so only one edge, only one interface, right, is going to be marked with an R. And the point is, if you sort of follow those R's, if I go from this node, I choose the interface marked R, and that takes me onto a LAN. I take any other switch whose interface is marked with a D, and I go into that switch. When I come out of it through its R interface, I'm closer to the root, and that's the property that the R's have. Okay. And then the properties that the D's have is that every LAN is just going to have one D interface turned on. So whenever I'm at a switch, if I take the R interface, I move closer to the root. It puts me on a LAN. Okay, and that LAN has some D interface turned on that takes me off that LAN into another switch, and I just follow that other switches, go out the R interface, and again I'm moving closer to the root. Sastry.
If you want to go with the root, yeah,
you'd start at a switch. You would take its R interface. That moves you toward the root. That puts you on a LAN. There's going to be one D interface turned on. Take that D interface. It brings you to another switch. It's got to be closer to the root than the original one. Then you take its R interface. So you keep following that process. Eventually you're going to wind up at the root node itself. Yeah, Ron.
Why can you say that it's at most one D attached to the LAN like that?
That's what we did in step 5. We turned out,
We had a broadcast on this LAN of all nodes that were transmitting D, and we turned them all off except one. So there's at most one. Okay? Okay, and remember, to do this process, in order to turn off the Ds on the LAN, such that there's only one D interface remaining on a LAN, we had this local message that was being broadcast locally on that LAN. Just every node attached to that LAN broadcasts its ID locally on that LAN. We're also going to have a global broadcast of IDs. So every node knows every other node's ID, okay, and the switch with minimum ID. is the root. So it's a very arbitrary process in terms of how we choose who's to be the root of the tree and which nodes keep their D interfaces turned on. You always favor the switches with lower ID. Okay, but it's very easy to run this as a distributed process, right? Basically, we continue to broadcast all our IDs, and we'll eventually learn who the smallest ID is, right? And we'll learn that it's in this example, it's some switch with ID number 2. And then we all focus our Bellman-Ford algorithm toward building a shortest path toward the node with ID 2. Okay, and then once we've built that shortest path, and we've got our R interface marked, then we're running this other protocol where we're broadcasting our ID on the local LAN. And if we see another node with the smaller ID broadcasting on that LAN, we turn off our interface. Yeah.
So if another switch is added that has a lower ID number, do they have to change the root then?
That will change the root. Yeah. Right.
So these LANs are used in practice, and these system administrators don't add switches every day, but once a week if they add a new switch for 5 minutes or 3 minutes or 2 minutes, depending on how quick it takes this algorithm to converge, your LAN will be messed up, won't work properly. Okay. But the point is, these switches have these algorithms built in, and it's all automated. So the guy doesn't have to program anything. You just plug in the switch. The spanning tree is figured out all by itself automatically, connecting up these LANs such that there's no duplicate transmissions and there's no, and it's always connected. And so even if a node fails, suppose node 5 is a bad example. Suppose node 4 failed. Okay, and it disappeared. How would that affect things? Well, the shortest path tree wouldn't change all that much because node 4 was a leaf. Just so happened to be a leaf on this tree here, but previously it was the node whose interface D, whose interface was labeled the D that stayed on. Now it's not there anymore. When these two guys do the local broadcast, this one's going to realize it's the lowest ID number and turn this interface back on. So it recovers quickly from failed switches as well. Okay? Any other questions on this? Yeah, Ben. Huh?
Process. It's spanning tree algorithm.
I think that's just what I call it. Spanning tree algorithm. Spanning tree algorithm for a LAN. Okay? That's really all the theoretical stuff I wanted to cover today. I really haven't talked much about the practical side of things. So let me go through some of that in the next 20 minutes or so. All right. No more questions on this. Okay. Yeah, David.
The roots are they're always turned on.
Yeah. You always keep your root interface turned on. Well, if you're a switch and you've only got N interfaces and all your Ds are turned off, then you're obviously not carrying any packets, right? I mean, a switch is really just a transmitter between two LANs. So it can just turn off the R as well. Any packets that come to it on its R interface, it's got no other interfaces turned on, it's not going to send them anywhere. So next it can be turned off. But otherwise, yeah, R's are always kept on. Patrick.
Say at most 1D LAN. Isn't there always 1D? Is there an example of finding not a D, just not 1D?
this LAN right here.
Sorry.
This LAN down here. These two switches both have Ds connecting to that LAN. Huh?
Oh.
Well, this switch here, this guy had two Ds. I mean, if a switch can be connected to more than just two LANs, you can have a switch connecting to several LANs. Every switch is going to have one R and several Ds. And every switch will have at most one active D. Oh yeah, this guy doesn't have an active D. He turns it off. Right? This LAN is only allowed to have one active D connected to it. No. Not after we made this change, where the root labels its interfaces with Ds. Then every LAN will have active D. Oh, wait, no, sorry. Suppose every LAN will have at most one active D, right? Because of that protocol. And will it always have an active D? Yes. Every LAN will have one active D. Okay. So this course is meant to be combined with 4119. So I tend to skip over a lot of the practical details, a lot of which are covered in that class. But let me go through some details which are relevant, which are necessary. Basically, I'm going to talk about addressing. Okay, remember you have this protocol stack: physical, data layer, network transport, application. Okay, and we've really been focusing on these two layers thus far. And devices. Oh, so here's homework 5. Devices have these identifiers such that they communicate on protocols that run at these various layers. Okay, this is something we sort of glossed over. So, if you remember, a switch only forwards information that it needs to forward from one place to the other. Right? This switch will only pick up information from this LAN. If I've got this device A, B, C, D, when device A sends to device C, okay, this switch will forward the information. When A is sending to B, the switch knows not to forward the information. And what we sort of glossed over is, how does a switch recognize a packet's coming from A or from B or from C or from D and going to A, B, C, D? So every device has an address. Okay, and let's talk about the data link layer. Has what's called a MAC address. Okay, and the MAC address is 48 bits. It is. Anybody know off the top of their head? I mean, MAC address is usually represented in hexadecimal, like 0A, 7B, 9461. I think it's 8-digit hexadecimal number, where each of these is 16. That's 2 bytes. 16 bits. Sorry, 0 through 16. That's 4 bits. So 4, 8. Each of these is 8. So 8 times 4 is 32. This isn't right. 4 bits, 8 bits, 1 through 4. Yeah, 2 more. Okay, it has 8, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's a 48-bit quantity. Where each 8 bits are represented as a 2-digit hexadecimal number. I should say each device. Each device has an address, each device has a MAC address at the data layer. Okay, so this is a 48 quantity because each of these digits is a 4-bit quantity, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, or F. Right, that's how you represent things in hexadecimal. People familiar with hexadecimal? Okay. So it's represented as a 2-digit, 8 bits are represented as a 2-digit hexadecimal number, and you've got 6 of them, with these colons separating them. Okay, so if you have a laptop or something like that, and you go to, with the exception of Columbia, you go to almost any other organization, and you want to get access on their network, they usually need to know your MAC address. Okay, if you have one of these wireless gateways at home, one way to secure access to it is you restrict the set of machines that are allowed to access your wireless device, and again, you provide the MAC address. Anybody familiar? Who's seen this sort of thing before? Just out of curiosity. Okay. So the MAC address is actually tied into the interface of the wireless or wired networking device. Okay, so a company has a certain prefix. A distinct prefix. It can assign to network devices it builds. Okay, so for instance, this isn't correct, but Intel's might be zero A, 0E, 17. Okay. So if this is Intel's prefix, then it's allowed to build devices where the first, 24 bits have this identifier. And then it has 2 to the 24 choices of how it can assign the last 24 bits, right? Giving each device it builds a unique identifier. And no other company is allowed to start with this prefix. I mean, that's standardized. So every device can be assigned a unique identifier. You should never find two devices with the same MAC address. Right? There are 2 to the 48 possibilities. That's 2 to the 10 is approximately 1,000. So it's 1,000 to the 5th power, roughly, which is like either 1,000 trillion or trillion. I mean, it's huge, right? You're not going to run out of identifiers anytime soon. Okay, So the MAC address is your device's identifier. It moves wherever the device moves. It's like your name. No matter where you go, you keep the same name, right? I'm Dan Rubenstein, whether I'm in New York or I go to New Jersey or wherever. Right now I live in New York. I could move to California. My name would still be Dan Rubenstein, or my social security number. That always stays fixed with me. That's how the MAC address works. Okay? And the point is, usually when devices communicate using the MAC address, there aren't that many of them. They're in some local region. So it's because you're in the data link layer. Devices that communicate over the data link layer are near one another. And let's just say easy to find. Right? I mean, if I'm giving you back your exams in this room, all I need is your name, and it's pretty easy to design the protocol where I give you back your exam. Right? Okay, at the network layer, each device is assigned an IP address. Okay, where IP is the protocol running at the network layer. And that's usually written in the form like 128.47.12.16. So each of these is a number between 0 and 255. Right? So again, you've got 256 times 256 times 256 times 256. That's 2 to the 8, 2 to the 32. There's 32 bits. 2 to the 32 possible IP addresses. And the critical difference between the IP address and the MAC address, again, the MAC address is fixed for your device no matter where you put it. IP address is like your apartment address. You live in New York. You have an address that's, whatever, 115th Street, New York, 10025. I mean, it's very easy. 10027. I don't know. It's very easy to locate where that address is. Right? It's as opposed to the MAC address, which moves around with the devices, and you take a set of devices in this room. The addresses that were given aren't correlated at all. You take a bunch of people who live in the same apartment building, and you look at their home addresses, and they're very highly correlated, right? They're all going to say New York, same zip code, same apartment, same street number, same apartment building number, right? It's a very structured addressing system. But the people who live there, they got their names. Their names don't change just because they live there. Okay? So if I wanted to give you, if we weren't all in this classroom, so for instance, the people on CVN, if I want to return their exams to them, it's not enough that I just know their name. I need an address to mail them a copy of their exam, or a fax number. The point is just using the name. I can't hand out to someone in the street and say, hey, get this to Joe Schmo, who's taken the course over CVN, and they won't know what to do with it. However, we have a system where we can give it to a postman with a specific address, and that postman knows how to route the exam back to the right person. So the IP address is like the apartment address, and the MAC address is like your name. Okay. So the way IP addressing works is that each organization has a domain of addresses. So for instance, Columbia CS uses 128.59 dot whatever. Okay, so any address that starts 128.59, that's Columbia University Computer Science Department, a machine on their network. Okay, so I take my laptop or I buy a new desktop. The new desktop comes with a network card in there already. That network card is already given a MAC address by whoever built it. Okay, I can hook it up within the CS department, and the data link level protocols can start operating right away, just using the MAC addresses. And then the CS department will assign it an IP address, 128.59. So now if I want to send something to this computer from very far away, I use the IP address. Okay, so you know here I am. I'll actually be in Philadelphia on Monday. Okay, so here I am in Philly. I want to check something on my computer. I have to use the IP address. Okay, from this Philly machine, it knows how to use the IP protocol. Professor Meeser will give a little more insight into how this is done on Monday. But using the IP address, it knows how to get to Columbia. Okay, 128.59. Whatever my machine's IP address is. All these routing protocols that we've used, distance vector and all that, can be used to find the shortest path between the machine I'm at in Philly and this 128.59. Okay. Any questions on this? Yeah, Faisal.
To avoid the same IP address to the machine, so how does that work? I mean, you use DHCP, right, to get the IP address, but then how does it work that you don't get?
So for instance, Columbia has administrative control. Columbia CS has control over this 128.59. There's a set of okay. So here's Columbia University. Let's say like this is ASIS. Okay, ASIS sort of controls all network operations at Columbia, and the CS department sort of branches off of ASIS, and they know that they have access to anything. ASIS reserves 128.59, the prefix for all machines in the CS department at Columbia. So now, the way it used to be done is you'd actually have an administrator keep a list of all machines 128.59.0.0, 128.59.0.1, and assign those particular machines. Now you have a protocol DHCP which does this automatically. I mean, DHCP is like a big database. It remembers which IDs it's already given out. But DHCP for the Columbia CS department knows it can only assign prefixes with 128.59. Okay. And it remembers for each prefix it's assigned, it remembers the MAC address for the machine that prefix has been assigned, that IP address has been assigned to. Yeah.
They only use two positions for the prefix?
Not necessarily. There's and actually what's going to be talked about on Monday is going to get more into this. But yeah, a certain number of bits is reserved for the prefix, and it's not really decided anymore in some organized means. There's a governing body, ICANN, which assigns prefix to big groups like Columbia. So I don't know what Columbia's prefix is, but Columbia's prefix will contain 128.59, and that part of it has been reserved for the computer science department. Okay, so the important thing is the IP addressing system is a lot more like is structured more like the the mail post office addresses. It's a very well organized system. It's machines that are near one another should have similar IP addresses, but they won't necessarily have similar MAC addresses. MAC addresses are more like name. And the reason is, when you use data link protocols, you can pretty much speak to everybody directly. So it's okay that we just use our names. Whereas IP addresses are used between machines that are far from one another. So you need to in order to exchange information between those two machines, you have to go through a series of routers or something equivalent to that, a series of nodes that are going to take the information from one point to the other. And you can't expect these nodes in the middle of the network to remember the location of every single device. There's just too many devices. So devices have to be grouped under some common structure, right? Like, just like if I want to send a letter to someone in Boston, right? The post office doesn't need to know the exact name of the person. You know, the post office that's located in Missouri or whoever, some intermediate round point. They just need to know, you know, they just look at Boston, Massachusetts on the bottom of my envelope, and they know which direction to send it in. Makes the routing a lot easier. So let's stop early. This will be picked up again on Monday. And I'll see all of you on Wednesday. Yeah?
So you said that switches connect LANs together.
Yep.
So and that it would use the MAC address to figure out.
Yeah. All this on the LAN, that's usually just done in the data layer. Right.
And so if there's fragmentation there as well, on the data layer.
Fragmentation.